Good morning. So today we'll discuss one of the application of permutations combinations, that is arrangements in groups, and how many ways we can divide distinct objects into groups. Distribution of objects into groups. Objects can be distinct or identical, two cases. So first one, number of arrangements of n distinct objects into R groups. N distinct objects into R groups. So first let's consider particular case. For example, there are say 5 objects. 5 objects into 3 groups. We need to divide 5 objects into 3 different groups. Groups means here distinct groups. So say like this one partition mark, this another partition mark. So we have 3 groups. First group 2, second group 1, third group 2. Another way, say here one partition mark, here one partition mark. So first group 4 objects, second group 1 object, third group 0 objects. So partition marks can be beginning or in between the objects, can be side by side. For example, both the partition marks here. So first group 4 objects, second group 0, third group 1 object. So both are different. Here third group 0 objects, here second group 0 objects. So all these cases, again the 2 objects here, the 2 objects can be these two, can be at these 2 places, can be these 2 places, anyway in the 5 places. So what we can do, so now let us look on how many objects in the arrangement. So there are 5 objects and including 2 partition marks, total 7. So 5 objects plus 2 partition marks. Now here we can consider the partition marks are identical. So we can interchange these two, still it is the same 3 groups. So that way, so 5 distinct objects, 2 identical objects. Total number of arrangements. 5 plus 2 factorial by 2 factorial, because partition marks are identical. So this is the total number of ways we can in which we can arrange 5 different objects into 3 different groups. 7 factorial by 2 factorial. Now same we can generalize for the n distinct objects. So we have total n distinct objects. To divide into R groups, we need R minus 1 partition marks. See, 3 groups, we need 2 marks. So n plus R minus 1. These are the total objects now. We can arrange this along a line. N plus R minus 1 factorial by R minus 1 factorial. Because the partition marks are identical. Whenever objects are identical, we divide with that factorial. So this is first case we are considering here. Each group can contain any number of objects. So in short, blank groups alone. Case 1, blank groups alone. Or like the group can contain 0 objects. Blank groups alone. Second, blank groups not alone. That means each group should contain at least 1 object. Blank groups not alone. So in this case, what we do, first we arrange the objects. Say we have n objects. N objects can be arranged in n factorial ways. Linear arrangement. If it is circular permutation, we know it is n minus 1 factorial. Now, so to divide this into R groups, so let's consider that gaps between the objects. N objects means including first and last gap, there will be n plus 1 gaps, but when we place partition marks here, the first group will be empty. So no group should be empty in the second case, blank groups not allowed. So let's consider gaps in between, not the first one and the last one. So there will be n minus 1 gaps. Out of these n minus 1, select r minus 1, because we are going to place only r minus 1 partition marks. We need to divide into r groups. So in the selected r minus 1 places, we can place the partition marks. That can be done in only one way because partition marks are identical. Therefore, by multiplication principle, n factorial into n minus 1 cr minus 1. So we are dividing the task into two parts. First we are arranging the objects and then we are putting the partition marks. So for arranging the objects n factorial and then for placing the partition marks n minus 1 cr minus 1. So this is the second case, blank groups not allowed. So here in case A, the groups, the objects are distinct, groups also different groups. Now when objects are identical, or before that say objects different but just distribution, no arrangement. Here we are arranging the objects inside the groups. Let's consider no need to arrange, just divide the objects into R groups. Divide n distinct objects into R groups. So after that we'll take when objects are identical, how many ways we can arrange in R groups, how many ways we can just distribute into R groups. Anyway, both will be same in that case. So how many ways we can divide distribution of n distinct objects into R different groups. R groups. Groups are different here. Again here also two things, when blank groups allowed, blank groups not allowed. Blank groups allowed. So each group can contain any number of objects. So when we take the first object, it can go to any number of any one of the group. So first object has R base to distribute. It can go to any one of the group. Similarly, second object has R base. Third object also has R base. So and so on, nth objects. So total number of ways R power n. So total number of distribution of n distinct objects into R groups or different groups where each group can contain any number of objects. In short, blank groups allowed, R power n. If blank groups not allowed, then we use principle of inclusion exclusion. So complementary way, we are going to subtract from total number of ways, subtract where some group is empty. Direct method, we need to divide into cases that will be lengthy. Say we have 5 objects and we need to divide into 3 groups. 5 objects. No group empty. Say consider minimum 1 object. So 1, 1 and then 3. Again, as objects distinct, these 3 can be any of 5. 5C3 ways we can select for this group. Again, so that the 3 can be in the first group or in the second group. So groups also different here. Arrangement alone we are not considering inside the group when we compare with the first case. Groups different, objects also different. Another case is there where our groups identical, objects different, objects identical, groups also identical. We'll see that later. So this one case, that means the distribution in this case will be select any one from 5, 5C1, and then from remaining 4 select 1, and from remaining 3 select 3. So as we are selecting any one, so again no need to arrange this into 3 factorial ways or 3 factorial by 2 factorial, not required. Because okay, what we are saying here, first group 1, second group 1, third group 3. Groups also different. Yes, we need to arrange the groups as well, 3 factorial by 2 factorial. Is that required? First, so with this what we are saying, first group can contain 3 objects or that one. Yes. So next, 1, 2, 2, total 5 objects. Next, minimum 2 means 2, 2, 2, it will be 6. So these are the 2 possibilities. Now here 5c1 into 4c2 into 2c2. Again same thing, into 3 factorial by 2 factorial. Because the one object, it can be in the first group, it can be in the second group, or it can be in the third group. That's why this 3 factorial by 2 factorial, we can arrange the groups. We can arrange. We are not arranging the objects, but the 3 groups. One object means it can be in any one group, and then that object can be any one of the 5 objects, because we are taking objects to be distinct. This is how we go with the direct method. But here, if number of objects more, dividing like this into cases, writing this selection and then arrangement will be lengthy process. So the complementary way here, blank groups not allowed. So from total number of ways, now subtract the distribution where one group empty. We have total R groups. Select any one group. We can select RC1 base. Assume that it is empty. No object is going into that group. So we need to send the objects to remaining groups. How many R minus 1 remaining groups are there? Remaining groups are R minus 1, because one group we are not selecting. So now how many ways we can distribute when we consider either blank groups or blank groups allowed, this case? So nothing but R power n, where R is the number of groups, here R minus 1. So R minus 1 power n. Now but the problem here is, we are going to subtract more ways, more number of ways. The reason, in RC1, it can be any one group. So consider the case R1 is empty, and then we are doing the distribution. So here assume that R2 also empty, because we are considering here blank groups allowed. So objects can go to R2 or may not go to R2, it may go to different groups. So consider the case where here R1 empty, here R2 empty, and then objects are going to other groups. Then in RC1, say R2 empty here, because it is any one group. We are selecting one group from R groups, RC1 base. And here in the remaining distribution, say R1 is empty. So both same. R1, R2 empty, here also R2, R1 empty. So we are subtracting more cases. That's why we need to add that. What we are subtracting more? Where 2 groups are empty. So add the cases where 2 groups are empty, which is RC2. Select any 2 groups. You distribute the objects into remaining groups. RC2 into R minus 2 whole power n. Again same thing happens here. We are going to add more cases, like where the 3 groups are empty. We are going to add 3 groups empty case more than once. So we need to subtract that, RC3 into R minus 3 whole power n, plus and so on, it goes till this becomes 1. After that it will be 0. 0 into anything, 0. So this is by principle of inclusion exclusion. So we are taking all possibilities. We are subtracting where 1 is empty. As we are subtracting more cases, we are adding where 2 empty, and then we are subtracting where 3 empty. Principle of inclusion exclusion. It's similar. In set theory also we use like n of a union b, n of a plus n of b minus n of a intersection b. The common elements we added 2 times, so we subtract once. Same we use in probability addition theorem. P of a union b, p of a plus p of b minus p of a intersection b. So that is the case here, and this we use to count the onto functions also. The same formula to find number of onto functions. Onto function means like every element in the codomain should have pre-image. So what we do, we count number of functions and we subtract the functions where like one object is not considered for the mapping, so that is not onto. The same logic. So this is a direct way, this is a complementary way. So we can replace that R value and value. So we get the number of ways of distribution of n distinct objects into R groups. Third one, where objects identical, groups different. How many ways we can distribute n identical objects into R groups? Here the arrangements just distribution will be same for identical objects, because identical objects we can arrange only one way. With respect to distinct objects, the arrangements and just distribution both are different, but with respect to identical objects, both will be same. So we have only 3 points. Actually, as per this, 4 points should be there, but both will be same for identical objects. So the third one, distribution of n identical objects into R groups. So it is same for the arrangement also. So we can go with that case A logic. So here again, blank groups allowed case. So what we did earlier, so n objects and r minus 1 partition marks we added and we arranged those. So factorial divided by r minus 1 factorial, because partition marks are identical. Now here objects also identical, so n factorial. So which is nothing but, we can write this as NCR notation, n plus r minus 1 cr minus 1, that is same as n plus r minus 1 cn, because NCR equal to NCn minus r. This is a number of ways in which we can divide n identical objects into r different groups. Here groups are different. So the same, we have multiple, the same formula, the question type will be multiple ways. Like the other way they can ask, we have 4 colors, balls of 4 different colors, and we need to select say 6 balls. How many ways it's possible? Each color, any number of balls from each color. So, or the other way, like how many non-negative integral solutions for the equation x1 plus x2 plus and so on xr, sum of r variables should be n, and here variables should take only whole numbers, non-negative integers can be zeros or natural numbers. Again same. So here objects means like ones. Here how many ones are there? Here how many ones are there? Total when we add it should be n. So that's like n identical objects, all ones are identical. So for this also it's the same expression. When we extend this, like when we have the constraint on these variables, say xr can take maximum. For example, if it is x1 plus x2 plus x3 equal to 20. Maximum possible value for x3 is just 15 only, it can't take beyond 15. Here there is no restriction, each variable can take 0 to n, any value. But there is some condition like that, then we have a different method. We use that binomial expansion for any rational index to find the solutions of this equation. Or like if it is some different coefficients are there, either some restriction on the possible values for variables x1, x2, x3, or there is some coefficients for variables. For such equations, to find the number of integral solutions. Integral solutions, there will be many when we include negative integers, but here the standard model is non-negative integral solutions or just in positive integral solution. That means variables are taking only natural numbers. Then we get the finite value as the answer. So for that model, we can go with the binomial expansion for any rational index. Different based on this method, it will be difficult, or when we want to divide into cases also, it will be lengthy. So based on this, let's take a question. Say we have 5 objects. Example, 5 objects 3 groups. So when the first one, objects distinct, groups different. So we need to place 5 objects into 3 groups, and then whether they are distinct or different, we have the conditions. First condition, objects also different, groups also different. In how many ways we can distribute the objects into groups? So we can use that point B, r power n minus rc1 into r minus 1 whole power n, like that. So here r is the number of groups, so 3 power 5 minus 3c1 into 2 power 5, or 3 minus 1 is 2, then plus 3c2 1 power 5 minus 3c3 into 0, it will be 0. So that is equal to, it is 243 minus 3 into 32 plus 3c2 is 3. So 246 minus 96, which is equal to 150. So there will be 150 ways in which we can distribute 5 distinct objects into 3 different groups. Second one, identical objects different groups. This one. So we need to divide identical objects into R groups, or different groups. So formula, n value, number of objects 5 plus R value 3 minus 1c 3 minus 1. So 7c2, 7 into 6 by 2, 2 factorial. 7 3 is a 21. N minus okay, one more condition I missed here. No blank groups. That's what we used here. Otherwise, it's simply r power n, which is 3 power 5. No blank groups. So in that case, here like same thing. Again, the second point, when groups are not blank. First, we arrange the objects in only one way because identical objects, and then we take n minus 1 gaps. Select r minus 1 from n minus 1 gaps because we need to place only r minus 1 partition marks. So that is the case here. So n minus 1 c r minus 1, 5 minus 1 c 3 minus 1, which is 4 c2, 4 c2, 6, 4 into 3 by 2. So distribution of 5 identical objects into 3 different groups. And where no group is empty, no blank groups. N minus 1 CR minus 1. Third case, different objects but groups are identical. Identical groups. There is nothing like first group, second group like that. So 5 objects we have seen earlier: 1, 1, 3, 1, 2, 2. Only these 2 cases. Now groups are identical. These 3 can be here anyway, but objects are distinct. So in this case, it's 5c1 into 4c1 into 3c3. That's all. Earlier we have whenever groups are different, we have written it 3 factorial by 2 factorial because this contains same number of objects. But that won't come here because groups are identical. So 5 4s are 20. Here 5c1, 4c2, and then 2c2. But here, as these two are, like we are saying, first group 5C1, next group 4C1, but they can be interchanged. Still, it is the same. So at 1 by 2, here also same thing, because these two are same. 1 by 2 factorial. So 10 here, 30 by 2, 15 here. So total 25 ways we can divide 5 different objects into 3 identical groups. We can't differentiate which group is which. No distinction between the groups. And the last one, both are identical. Identical objects, identical groups. Again same thing. No, here no group is empty. Same 1 1 3 1 2 2. And then here this 5C1 4C1 won't come because objects are identical. We can do only one way. The selection will be only one way. So this is one possibility. This is another possibility. Again further group arrangement also not there. Groups also identical. Only 2 ways. Answer is 2 in this case. So distinct, both are distinct, any one distinct and one other one identical, and then both identical, the 4 cases. So for these two we can directly use the formulas. For these two we need to go with that, okay, writing the cases. Thank you.